modeling geometry distributions. For example, when you roll a die, that is a very good example of a discrete uniform distribution, and it's called discrete because the outcomes are countable, and it is uniform because the probability that every outcome takes, for example, getting a 1 is a probability 1 over 6, getting a 3 is a probability 1 over 6, and so on. Similarly, an experiment having only two possible outcomes, right or wrong, head or tail, 1 or 0, is a good example of a Bernoulli distribution. So what we'll do today is talk about how different discrete distributions can be used under different settings. So what we'll talk about is we'll talk about different stories or different descriptions for every distribution and how these stories relate to these discrete probability distributions as well as continuous probability distributions. More often than not, the situational stories are more commonly used for discrete distributions. When you hear a scenario, you'll immediately be able to relate it with a certain discrete probability distribution. Let's once again summarize the most commonly used discrete and continuous probability distributions. So our goal for this module is to go over this material, and for the next module is to cover this material, and we'll try to solve a few examples in Excel. That way you're familiar about how to use Excel for tackling these problems, because sometimes these problems may become rather complicated when you're trying to solve these manually. So we'll talk about using Excel, and throughout this course we'll try to use Excel for solving different types of problems. So going back to discrete probability distributions, there are what is known as a Bernoulli distribution, binomial, geometric, Poisson. You have discrete uniform, which we briefly talked about. You have negative binomial and hypergeometric. And these are the most commonly used ones, not to mean that these are the only discrete probability distributions. There are several others, but we'll just focus our attention, in fact, only on these four, the first four. So what I want you to do is refer to any common, one of our reference books that you see in the syllabus copy, and you'll be able to find these 5, 6, and 7, and I want you to do a self-study for those things. On the continuous probability distribution side, once again, I'll go over only normal and exponential, and I'll expect that you will go over continuous, uniform, Weibull, and Erlang by yourself. So what we'll do is we'll now begin with Bernoulli distribution. Now let's look at Bernoulli distribution. If random variable x describes the outcome of an experiment with only two possible outcomes, it can be modeled as a Bernoulli random variable. And the mass function is written very simply as this: f of x is p if x equals 1, and it is 1 minus p if x is 0, which means that there are only two choices. For example, when you toss off a coin, you either get a head or you can get a tail. Does it rain or shine today? Do you win or do you lose? Packers or Bears? Brewers or Cardinals? So these are really when an experiment has only two choices, when you have only two discrete choices, these are really discrete choices. You can either win or lose, 1 or 0. So it's really a binary decision variable that you're talking about. It's either 1 or 0, head or tail, true or false, win or lose. So these are all situations that can be modeled using a Bernoulli random variable, and it's the simplest form of a random variable or a probability distribution, a discrete probability distribution. Now let's talk about a binomial distribution. A binomial distribution is really a collection of n Bernoulli trials. If x describes the number of successes or failures from n Bernoulli trials, it can be modeled as a binomial random variable. So what it is if you are conducting several or n Bernoulli trials one after the other, then that random variable can be modeled as a binomial random variable. And if that random variable is talking about either the number of successes or failures from your experiment, from your n Bernoulli trials, The properties of binomial, we'll come back to this distribution in just a second, but let's just go over the properties of the binomial distribution. The probability of success or failure in each trial is the same across all trials, which means P is the same for each trial. If your P changes for every trial, then it cannot be modeled using a binomial random variable. And these trials that you have, the n trials, need to be independent, which means the impact of, there should not be any impact from one trial to the next. For example, when you're tossing a coin 20 times, these are all individual independent trials, and the fact that you got a tail on trial number 2 does not influence the outcome of trial number 3 or trial number 4 or trial number 5 and so on. So these are really independent trials, and the probability needs to be the same in every trial, and then you can model this situation using a binomial random variable. And f of x, which is really the number of successes or failures, can be written as n combination x. This is written, this read as n combination x or ncx. This can also be written as ncx, or really n factorial divided by n minus x factorial times x factorial. If you remember your permutations and combinations from high school, that is what this is, n combination x multiplied by p raised to x 1 minus p raised to n minus x. So a good way to remember this is ncx multiplied by probability of success raised to the number of successes multiplied by 1 minus probability of success raised to or 1 minus probability of success, really number of failures, raised to the number of failures. So keep this in mind. This is an easy way to remember a binomial distribution, or the density function of a binomial random variable. Binomial distributions have several uses, and it's a very practical distribution. It's often used in quality control when an inspector is doing quality inspections of number of products. If they want to find out how many defectives there are in a batch of 100 or 200 products, then a binomial distribution can come in handy to compute these probabilities. Then public opinion surveys, how many people are voting one way or the other. Then in medical research, insurance problems, whether an individual is risky or not. Sampling items in production lines, once again related to quality control. Estimating failure rates or percentage of failure rates of products and components, once again a quality control related example. So there are several applications of binomial distribution that can be used in real life. So let's take a practical example of a binomial distribution. If 20 electrical fuses If 20 electrical fuses are randomly sampled from a large set of fuses, what is the probability of finding at least 3 defectives, where the probability of finding one defective is 5%? So how do you answer this question? So let's see here. Your n, the number of samples, is 20, and the probability of your finding a defective is 5% or 0.05, and they want you to find probability that x is greater than or equal to 3, which means technically I have to find probability that x equals 3 plus probability that x equals 4 plus probability that x equals 5 plus etc., all the way up to probability that x equals 20, because even finding 20 defectives also satisfies this condition. So the other easier way to do this is simply solving 1 minus probability that x is less than or equal to 2, or in other words it can be written as 1 minus probability that x equals 0 plus probability that x equals 1 plus probability that x equals 2. So if we can compute these values, then we'll be able to find the answer for this problem. So how do we answer this question? Once again, go back to the density function. The density function of a binomial random variable was n c x p raised to x 1 minus p raised to n minus x. So we can use the same density function for solving this. So this essentially boils down to 1 minus probability that x being less than exactly equal to 0, probability that x equal to 0 is nothing but nc0 p, which is 0.05 raised to the number of successes. In this case we want that to be 0, multiplied by 0.95 because it's 1 minus p raised to 20 minus 0, which is 20, plus we have nc1 multiplied by 0.05 raised to 1 plus, multiplied by 0.95 raised to 20 minus 1, which is 19, plus nc2 0.05 raised to 2 because we have x equals 2 multiplied by 0.95 raised to 20 minus 2, which is 18. And here remember n is 20, so when I say 20c2, all this means is 20 factorial divided by 20 minus 2 factorial multiplied by 2 factorial. So remember that when we are talking about those values, this 20 here. Okay, so I hope you'll be able to calculate this, and this can be easily done using either Excel or just punch these things in your calculator. Now let's take a look at another example from binomial distributions. The problem says a fire detection device utilizes 3 temperature sensitive cells acting independently of each other in a manner that any one could actuate an alarm. Each cell has a probability of 0.8 of actuating when temperature reaches 100 degrees Fahrenheit. Find the probability that the alarm will be triggered when the temperature reaches 100 degrees. At this point, take a few minutes to see if you can set this problem up, and then come back to the lecture and let's try to solve it together. But I want you to first take a break and try to see if you can solve this problem by yourself. Okay, so I hope you have tried how to solve this straightforward problem. So here we have once again an application of binomial distribution. So we have 3 cells, and the alarm can be triggered by any one of these cells actuating. So each cell has a probability. So the probability of actuating is 0.8, and when the temperature reaches 100, one of these cells can actuate. So they want you to find probability that the alarm is triggered or actuated. And the alarm is actuated when at least one actuates, or can I say probability that x is greater than or equal to 1, which means I can either do probability that x equals 1 plus probability that x equals 2 plus probability that x equals 3. So this is one way of looking at it. Or the other easier way of looking at this problem is 1 minus probability that x equals 0, or in other words, you're trying to find out the probability that there is no alarm, and 1 minus that would tell you how many cells have actually functioned. So you can do it this way as well. So 1 minus probability of the alarm not going off, so which means 1 minus, once again you have 3 cells, so that will be 3C0. Probability of you want it not to actuate, so which means that is 0.2 raised to 0 and 0.8 raised to 3. So that will be the answer for this problem. Oh, just a slight correction here. This needs to be 0.8. So let me just try to strike this off. And let's just write this again here. It's 1 minus 3C0, 0.8. So that hasn't changed. 0.8 raised to 0, which means you want 0 successes. And 0.2 is a percentage for failure raised to 3. In other words, that will be 1 minus 3C0 is simply 1 because it is 3 3C0 is 3 factorial by 0 factorial multiplied by 3 factorial, which is nothing but 1. So this will just boil down to 1 minus 0.2 raised to 3, which is 0.008, or in other words, this will be 0.992. So I hope that was okay. Initially what I said was I asked you guys to take a look at 0.2 raised to 0. It should really be 0.8 raised to 0, but nothing else changes because we still have 0.8 here. Okay. Alright, so now let's look at another example. Now let's move on to geometric distribution. Once again, I just want to restate here that all of these, or most of these discrete probability distributions, are from the same family, which is really the binomial family. All of these distributions are related to binomial distribution. If a random variable x describes the number of experiments needed to get the first success, it can be modeled as a geometric random variable, and the density function looks like this. And we'll take a look at the density function a little bit. I want you to first pay attention to the story behind this distribution. If you're looking at the number of experiments needed to get the first success, for example, if NASA is conducting a series of experiments or series of tests, it's inspecting a product and it wants to stop, it has a zero tolerance policy and it wants to stop the moment it finds a defective, then that kind of an application can be modeled using a geometric distribution, because you're really talking about the number of experiments needed to get the first success. First success or first failure, it doesn't matter. Really, the first event that you are interested in as a modeler. And that can be written as f of y is p times 1 minus p raised to x minus 1, where x equals 1, 2, or 3, and 0 elsewhere. Once again, these are discrete probability distributions, and they do not take values at every point. They only take values at discrete time points. The mean of a geometric random variable is 1 over p, and the variance of a geometric random variable is 1 over p divided by p squared. Here there's an example for a geometric distribution. It says find the probability that it will take a total of 10 trials to get the first success. 10 trials to get the first success, and the probability of each success has been given to be 0.1. So in this case, how do we find that probability? So which means that I should have had 1, 2, 3, 4, 5, 6, 7, 8, and 9. I needed to have 9 failures. And then finally the last one is a success. So if I have 9 trials and I have to get 9 failures, once again that's a binomial distribution, isn't it? Can I simply write that as 9C0 p raised to 0 1 minus p raised to 9 minus 0 multiplied by the probability of one lone success, which is p. So this is really 9C0 is 1, anything raised to 0 is 1. So this boils down to p multiplied by 1 minus p raised to 9 minus 0. And this is exactly what you have on the previous slide, which is p 1 minus p raised to x minus 1, where x is your total number of trials. The total number of trials for us in our specific problem, the x was 10. So p multiplied by 1 minus p raised to 10 minus 1, which is exactly what we have here. So once again, geometric is also related to binomial. Now let's take a look at Poisson distribution. Poisson distribution, it was invented by the mathematician. His name was Denis Poisson. So it is not a Poisson distribution, it's a Poisson distribution. It's the name of a mathematician. So once again, this has an interesting story. If x describes the number of successes or failures from a very, very large number of trials, it can be modeled as a Poisson random variable. So what it really means is if your sample space is very large and probability of occurrence of events is very, very small, then we can model those scenarios using a Poisson random variable. If the sample space is very large but the probability of occurrence of events is very small, for example, the number of misprints in a book, obviously the sample space is a very, very large number, but how many misprints do you actually find in a book? Very few. Similarly, number of customers at a bank on a given Monday morning. The number of customers for a bank could be 10,000 or 20,000 or 30,000, but how many people actually show up at the bank on a given Monday morning? So the sample space is very large, but the probability of occurrence of a specific event is very small, and that scenario can be modeled using a Poisson distribution. And the Poisson distribution, it may appear a little complicated, but it is not really that complicated. F of x is lambda raised to x, e raised to negative lambda divided by x factorial. For x is 0, 1, 2, 3, which is once again a discrete random variable, and lambda being greater than 0, where lambda is the rate of something happening or not happening, the rate of occurrence of something. Okay, lambda is always the rate of misprints in a book, the rate of arrival of customers, rate of service of customers, rate of accidents. So lambda is always the rate, and once again x takes discrete values, and once again it's 0 in all of the places. That's why it's called 0 elsewhere. Just like all other previous discrete distributions, Poisson is also related to binomial. Let's see how it is related to binomial. When you take the limit n tending to infinity for a binomial distribution, it starts to look like this. So I want to assign you guys a homework problem. So I want you to do some research and prove this aspect. It is part of your homework number 1, where you have to prove that as limit n tends to infinity for a binomial random variable, which is given right here, binomial distribution, it tends to Poisson distribution, which is lambda raised to x e raised to negative lambda divided by x factorial. So try this out at home, and that'll be part of your first homework set. Now let's look at a practical example for a Poisson distribution. And this will be one of the most commonly used distributions that you will see if you are studying operations research 2 within our department, which is really stochastic OR or probabilistic OR. There's one of the most commonly used distributions. Poisson distribution is related to exponential distribution, and we'll talk about that in just a second, but let's just go to this problem. Electricity failures occur according to a Poisson distribution with an average of 3 failures per 20 weeks. Calculate the probability of less than or equal to 1 failure during a given week. So they're giving you the rate per 20 weeks, and they're asking you a question based on 1 week. So how do you answer that question? Poisson distribution has this interesting property. If you have 3 failures in 20 weeks, the rate in 1 week is nothing but 3 divided by 20. So the new lambda is really 3 over 20. So Poisson distribution allows you to change this lambda based on what time unit you have. So I can also compute it for 2 weeks, I can compute it for 3 weeks, I can compute it for 4 weeks, and so on and so on and so on. The value will not change. So now I've been asked to compute probability that less than or 1 failure occur during a week, which is x less than or equal to 1, which means that is equal to probability that x equals 0 plus the probability that x equals 1. So how do you handle probability that x equals 0? So how do I solve this problem? Try to take a minute to see if you can solve this, and we'll come back and solve it together. So probability that x equals 0, probability that x equals 0 equals lambda raised to 0 e raised to negative lambda divided by x factorial. Or in other words, lambda is nothing but 3 divided by 20 raised to 0 e raised to negative 3 divided by 20 divided by 0 factorial plus probability that x equals 1, which is nothing but lambda raised to 1 e raised to negative lambda divided by 1 factorial, which is nothing but 3 raised to 20 e raised to negative 3 over 20 divided by 1 factorial. So when you sum this plus this, so when I sum this value plus this value, I will get the answer for probability that x is less than or equal to 1. So that's how you solve an example for Poisson distribution. Here is another example for a Poisson distribution. Vehicles passing through a busy road junction are distributed Poisson with lambda equals 300 per hour. Find the probability that no vehicles pass through this junction in a given minute. So once again, you got to switch that lambda and try to find out. And I want you to once again solve this problem by yourself, and we can discuss the answer if you have any questions. Now let's go to this switching that we talked about. Remember that lambda can be changed by changing the unit of time. For example, if x equals a number of calls to a switchboard in 1 minute distributed Poisson with lambda equals 3, then y, another random variable, can be defined which is number of calls to a switchboard in 5 minutes, where lambda is nothing but 15. Similarly, I can define another random variable called z, which is number of calls to a switchboard in 10 seconds with lambda equals 0.5. So the initial lambda equals 3 was changed for 5 minutes. For 1 minute if it's 3, for 5 minutes it is 15, and for 1 minute if it is equal to 3, for 10 seconds it is 0.5. So this can be the advantage of Poisson random variable, is that the lambda can be varied based on the need of the problem. In the next module, we will take a look at how to solve each of these problems using Excel. That way you're ready when a larger problem of a larger scale needs to be solved. So at this point we'll stop this module, and in the next module we'll pick up with solving for discrete probability distributions using Excel, and then we'll continue on to continuous probability distribution functions. Thank you.